Assalamu alaikum. This is a short lecture on digital PID controller. Considering we have a parallel form of the PID controller, we can uh, we can represent the valve position, the controller output, as PT, and we have a BICE term here. This is a steady state, assuming that the process we are having the process at the steady state. This is like a steady state, and this is the value. This is a steady state, and what we have is a constant value of the valve, and after that there might be some error, might be if we consider with respect to the time, and if this is some kind of a load or disturbance. We can assume that the load is, for example, a constant load of 10 or 25%, and suddenly it changes to, let's say, 50%. So this change will cause some error, and due to the error the steady state will be disturbed, and the next steady state value might be this. So our controller will be responsible, and it will move in between this, might be overshooting like this one, or it may go, for example, smoothly like this, okay, to the new value. And therefore in this video we are going to see step by step how the digital PID controller is going to work. So coming back to the starting equation, the parallel form of the PI controller, where we have a part of this part of the Kc delta E multiplied by the E error, and this is the term for the integral. PT is the controller output, Kc is the controller gain, E is the error, which is the set point minus the process variable or the control variable, and we have the time Ti as the time integral time. To avoid any confusion, it's better to assume MT and instead of the PT, to avoid the P that we are going to use for the controller. Therefore, rewriting this equation will be written as MT equals to this is the BICE, or the steady state value of the controller output, and this is the corresponding to the proportional term, and this corresponds to the integral term. And here our aim is to find the velocity form and the digital implementation of the PI controller. So we are going to find the digital equation of the PI controller, starting from the equation MT equals to M bar Kc Et 1 upon Ti integral of Et dt is the PI, and this is called position form because the controller output is actually giving us the required position of the valve or the final control element. It's to find out the velocity form, it's better to differentiate the both sides. So we differentiate and we get dm upon dt, and this is a constant term. Differential will be 0 for this. Kc differential of the error, and then the integral is differential will cancel out the integral. Finally, we replace the differential by the finite difference approximation, and by the next value minus the current value divided by this, or the current value minus the previous value, ek minus 1 divided by delta t. This is going to be like the approximate differential between the two samples. Here delta t is basically the sampling period, which is the time between the successive measurements of the control variable, and ek is the error at the kth sampling instant for k equals to 1, 2, 3 and onwards. We have ek plus 1, which is the error at the k plus 1th sampling instant. Before moving, so we have the equation here. this is delta m divided by delta t equals to kc, and delta E upon delta t plus 1 upon ti e of k plus 1. K plus 1, you can think of k plus 1 is the current value of error, and therefore the previous will be E of k. By this multiplying, taking delta t on the other side, we will arrive to the equation number 1. And this equation, the advantage of this equation is this equation can be used to calculate the delta m, that is the difference between the current and the previous movement of the delta m. And second point is we can also calculate the next movement with respect to the previous one, and it applies to any two instants in sequence. In the slides we have this is slide number 31, which is on this uploaded slides. Here we can compare. Actually, E of t is basically E of k plus 1, and E of t minus 1 is basically E of k. So here we are using k instead of t, and we can compare this. Mt is basically mk plus 1, mt minus 1 is basically mk, and et is ek plus 1, et minus 1 becomes E of k, and et is basically ek plus 1. So we have this simple equation of pi in the velocity form. Next, move to the how the digital implementation of PID, especially the PI algorithm, is going to work. So in the current scenario, in this equation, here this equation will be used. This is the digital implementation of PI algorithm, starting with the condition that kc is 2, ti is 5 minutes per repeat. Controllability is initially at the steady state of 40%, and this can be treated as m bar, or this is also mk. Controller frequency is 1, so we have delta t equals to 1, and assume that there happens 3 load changes, and which cause the error to change from 10%, 5%, and 0%. So on the x-axis we have time here, and on the y-axis we have the error. So initially the system is at a steady state, and then some load changes occur, and during this load changes, the first few instances we have 10%, next 5%, and finally it is 0. So we are going to study how the PI controller is going to react. And this so we have this equation mk plus 1 minus mk equals to kc, and then we have delta E plus the integral term here, delta t upon ti e k plus 1. So given this all values from kc to 5 and 40% delta t, and using this equation we should be able to solve the values for case the p and I, and the value of p is basically kc delta e, and value of I is kc delta t upon ti e of k plus 1. And our job is to find the values of all the values of delta e, p, I, delta m, and m of k plus 1. This is the simple solution. Initially we have the values. We have of course the first time we have all these values of first two columns, having 10% load change, 5% load change, and for the and this is the first one is our steady state. This is our steady state, and So at step 1, this place at step 1, we calculate delta E, which is equals to E of k plus 1 minus E of k, 10 minus 0. So we have a value of 10. We will be able to calculate P, which is Kc delta E, and it gives us the value of 20. So we have 20 here, and similarly we can calculate I, which is Kc delta T upon Ti E of k plus 1, and we calculate it as 4, and this makes us to calculate delta M, which is the addition of P plus I, and it gives us the value of 24. So the valve is going to move around 24%, and previously it was at 40%. So the next value, M of k plus 1, is equals to 64. Step 2, we have delta E. Now this time we can see that the current value is 10, the previous value is 10, so the answer is 0. Because of this answer, the proportional is going to contribute nothing, and the integral will be calculated as 4 here. So we have a 0 error, proportional is 0, integral is 4, so delta M is going to move around 4, and adding with the previous 64%, the next movement is 68%. Same happens for the next stage, and 4 is added at the step number 3, and we have around 72% at 3, 76% at step 4, and so for these, if we see, the integral is constantly added during this sustained error. Error is sustained, and after that is step number 6. The error is changed now. Error is changed from 10 to 5. So 10 to 5, we have an error of -5. The proportional is came back into action. Whenever there is a abrupt change, proportional is going to make some action. So it is -10 here. Error was -5, and the integral is around 2, which is calculated. and delta M is going to be P plus I, so it is -8 now, and we have the next value around -8 plus 80%, 72%. Step 7, again the error is now 0, so proportional is 0 again, and the integral is still 2, and adding to the previous value, it becomes like 74%. Error remains 0, delta E remains 0, and the proportion is 0, integral is 2, and 76, and finally we have the value. The same goes with the 9. The error this time is -5. -5 makes a proportional of -10, and error currently is 0. So error is 0, so integral is going to be 0 this time, and all the contribution from the proportional this time 66%, and the error remains 0. So this time we have since the error difference is 0 as well as the current value of error is 0, so in the end we stayed at. So for the last 2 steps, the valve is now stabilized. Filling out this table here, we have all these values we just filled. So this way we are able to see step by step how the integral term, how the integral and the proportional individually are contributing at each step depending on the error and delta E. The next slide, it's showing us the interesting view about the controller output. This is the disturbance that we have. This is the load disturbance, and when the disturbance occurs, initially it was at the steady state of 40%, and after this load change and the error, we have a change of the delta m. So the first time it was huge, 24%, and successively for the next 4 steps it was 4% added by the I only. And next we have a change in the error, and the proportion contributed around -8. Next we have the valve movement of 2% for the 2 steps, and finally a contribution by the proportional, and the system is stabilized here. Now we just try to note down the starting point was 40%, and now it is staying at 66%. So the valve steady state is shifted. So the valve or the final control element steady state position is now shifted to a new bias value. So this is the old bias value, and now this is the new bias value, and this is how the controller is able to act against any load disturbances. Thank you.